and that is we will be recording this session today, and we'll be in contact with you so you have a link where you can go to either stream or to download the presentation with video and audio, such that you can take another look yourself, or can maybe share it with some of your colleagues that might think it's of interest. So we'll send you an email, usually within a couple of days of the presentation completing. And in that same email, you will see a PDF file containing the slide set from the presentation. So just to let you know, there's no need to request one from us. You'll automatically get PDFs of the presentation today. Welcome to this Fluke web seminar, How and When to Use Fast Pulses and Sine Waves for Calibrating Oscilloscopes. I'm your presenter, Paul Roberts, and my colleague Rich McFadden will be hosting the event today and taking care of any comments and questions that I hope you'll be sending us during the course of the presentation. So let's make a start. You know that oscilloscopes are being introduced to the market quite rapidly now, with ever-increasing bandwidths, higher and higher performance and bandwidths. It's quite common now to see scopes in the several gigahertz or tens of gigahertz region, and even the typical lab-type scope now is probably under 1 gigahertz scope, where in the past it used to be perhaps a 100 megahertz scope. So there are higher frequency scopes come into the calibration workload. When I go around and talk to the users in the Cal labs, they tell me that the majority of their workload is still sort of in the region of perhaps up to a gigahertz, maybe up to 2 gigahertz. They do see a few of the much higher scopes coming back for calibration, but most of those tend to find their way back to the original manufacturers. However, there's still quite a few of the lower traditional sort of 100 megahertz, 200, 300, 400 megahertz scopes appearing in the workload as well. And when we look at the requirements for calibrating an oscilloscope, we will find both bandwidth tests and pulse response tests. So there will be time domain and frequency domain tests of the scope. And typically you will use a level sine wave for the bandwidth test and a fast pulse for the time domain tests. Now, it is actually possible to calculate a bandwidth or an equivalent bandwidth figure by using a rise time test performed with a fast pulse, and that will give you an equivalent bandwidth, which is often faster test to perform and can be quite convenient if you don't actually have a high frequency signal source around, or your oscilloscope calibrator doesn't go high enough in terms of its level sine wave output to achieve the bandwidth you want for the particular scope you're calibrating. So what we're going to do today is to take a look at these topics, starting with a brief introduction to oscilloscopes and calibration. Then we'll take a look at why we have both of these types of tests being performed and how the tests are performed in both the time and frequency domains, and what are the most appropriate methods for doing so, and take a quick look at some of the considerations and implications. During the presentation, I'm going to make a reference at a couple of points at least to some of the future topics in a series of 3 presentations. In particular, the last topic, which you can see here on the right-hand side of the slide in that box with the sort of pale yellow color, where we'll be dealing with some of the uncertainties and error sources in the high frequency calibration areas, where in fact we're crossing over from what's generally thought of as the DC and low frequency world for scope calibration into the domain of RF and microwave calibration. So for any of you participants that are not used to some of the principles and practices of RF and microwave and some of the terms we'll be talking about, there'll be an opportunity there later to get some more detail. In today's presentation, we'll only have time for a fairly brief coverage of those particular items. We'll be more interested in what their implications are rather than the principles behind them. Start by just taking a very quick look at the types of scopes that we have around in our labs and in the calibration workload. Sitting at the top there on this slide, the good old analog scopes. Surprisingly, there's still quite a few of them around. You can buy them now cheaply if you're into simple scope that you need for just simple work or perhaps education. And the scopes, as you can see from that simplified diagram, make use of a cathode ray tube and actually deflect a beam of electrons on the tube to write the trace. They actually have one single beam, which is usually split between 2 or possibly even more channels. Those channels will generally have at least a 1 mega ohm input and sometimes a switched 50 ohm input as well to provide a 50 ohm termination. All the scopes have actually 2 beams, 2 electron beams, so they can provide better display 2 channels or multiplex up to even more. Then we move down onto the real-time digital scopes. That's the majority of scopes we say these days, even going up to in the region of 30 gigahertz and above. Now, many of these scopes in the lower frequency ranges will have 1 mega ohm and 50 ohm inputs, but the higher frequency models will only have a 50 ohm input. That's necessary to achieve the higher frequency performance. Their architecture is quite different. They make use of analog to digital converters to convert the signals coming in real time, store them into their memories, and then pull those signals out of the memories in digital form and press that digital information to reconstruct a waveform on the display or to provide the various readouts and other analytical functions that they have. And the digital signal processing that's used in those scopes is often used to extend the bandwidth as well, often through a scope with an entry-level bandwidth which you can then increase its bandwidth by purchasing a license option from the manufacturer. Those scopes can deal with any kind of signal, a repetitive signal or a single one-off event. But the sampling scopes down at the bottom of the screen are somewhat different. They again have a different architecture. They make use of analog to digital conversion, but in front of those analog to digital converters, we have samplers, take sample and holds. And they use a principle called equivalent time sampling, where they take samples on successive cycles of the input waveform at slightly later times, so they can actually reconstruct the overall waveform. You are actually running a lot slower than the waveform itself. In other words, they can provide a display of a high frequency signal at higher frequencies than the ADCs could otherwise digitize. They commonly make use of sampling heads because of the high frequency problems of getting in cables and other interconnections into the samplers. The samplers are usually held in little pods on the end of cables. As I said, those scopes must have repetitive. Their input ranges are generally a little bit more restricted. However, there's some other features that we should just briefly mention here, which are of interest to us. And the first one is the one at the very top of the slide, which is another technique for providing very high bandwidth scopes. This is the dual bandwidth interleave scheme, which is a principle which you can see in that block diagram there, where we split the input signal into 2 more frequency ranges, down convert them, so that the ADCs are operating over a restricted bandwidth than the entire signal capture bandwidth. That means you slower ADCs, then restruct some clever digital processing back to a wave that the equivalent of the input signal back into the time domain effectively for display on the instrument's display or for any other kind of measurements with cursors and signal analysis. And that at the moment we are seeing scopes from a range of about 30 up to probably in excess now. I think I saw something in the region of 80 gigahertz where you can split the available bandwidth, so perhaps you can have, as we see there, 2 channels of 36 as a dual channel, or 1 channel of 65, and so on. So you can divide up and get multiple channels with lower bandwidths, or 1 channel with a very wide bandwidth. Now, those are a bit out of the context of this presentation, but I've included them there for information. The bottom 2 are actually the kind of scopes that we are seeing in the workload, especially the one in the middle, the mixed signal oscilloscope, which is basically a real-time digital scope with additional logic channel inputs, a bit like having a logic analyzer built into the scope. So the scope part of the instrument would be calibrated very much like a regular scope, and the logic channels are very simple because they are 0 to 5 volt or similar type logic level signals, and the calibration for requirements of those are really quite simple because they're not involved in any particular accuracy other than being able to distinguish between a 0 and a 1. The key, however, with those scopes is there is a time rate relationship preservation between the scope channels and the logic channels, so you can actually see what's happening on your side as well as on your analog side when you're testing your circuits. And of course, one of the really important things we're interested in calibrating oscilloscopes is because they are very much testing items. They are measuring instruments, not just for a display of a waveform, because they have all of these analysis features, cursor readouts and so on. They are measuring instruments used to measure all sorts of quantities, and therefore we need to be sure that they're giving us the right answer, and we do that by verifying their performance against specifications through the process of calibration. The one at the bottom is the mixed domain oscilloscope, which is basically a combination of again, a regular real-time digital oscilloscope and spectrum analyzer. So it's a separate RF input for the spectrum analyzer circuitry, and once again, through some clever architectural, especially on the digital side, the timing relationships are preserved between the 2 displays, which can be very important. And as far as calibration goes, the oscilloscope portion is calibrated like an oscilloscope. The spectrum analyzer portion is calibrated like a spectrum analyzer. And that's something which shouldn't cause too many problems for regular calibration. And I use the term regular calibration or routine calibration to mean the process of confirming the correct operation against specification, in other words, performance verification, the sort of activity that you would carry out on a routine, perhaps annual basis for the scopes as a self-supporter, where perhaps an in-house calibration facility or a third-party calibration service provider would perform. The scope manufacturers have somewhat more sophisticated requirements, and indeed they do, in the manufacturing test and the testing after service and repair for the oscilloscope products. And we'll kind of touch on a little bit how some of those requirements go a little bit further than the things we're discussing today, right at the very end of the presentation. A couple of more slides just talking about oscilloscopes and some important aspects of scopes that are relevant to what we're talking about today. And the first one is the idea of having a switched input impedance. Typical now, you would have an input which would either be 1 megohm or 50 ohms, and you'd select that through usually one of the menus on the scope. On the older oscilloscopes, there might be some actual mechanical switches on the front panel, but you can see I've given you a screenshot there of one of the popular scopes and the kind of controls. The scope is designed to have a 1 mega impedance, to have a low capacitance as possible, usually somewhere in the region of 10 and 25 picofarad. The higher frequency models tend to have a capacitance than the frequency models. But when you want to create a 50 ohm input inside the scope, you have to switch in a 50 ohm termination. Now, the oscilloscope designers have quite an interesting set of problems and compromises here to be able to provide a very good 50 ohms that doesn't get degraded by the effect of that parallel capacitance when the 50 ohm termination is selected. And that can be more a problem with the higher input capacitance circuits, and that typically, as I said, is the lower frequency scopes, where it tends to be less of a problem, but nonetheless it does cause some issues, and the designers of the scopes do their best to work around that, often by incorporating compensating networks, which inevitably mean there's some inductance added into the circuit deliberately to nullify the effect of the capacitance, which means the scope response can have some peaking in order to obtain the overall input condition looking as resistive and as good 50 ohm as possible, which means we might see some king and dip in the frequency response. And I'll show you some examples of that later. And of course, the other issue is that bandwidth is often very important, and stretching the bandwidth of the design as far as possible also requires some of these techniques to be employed as well. So input impedance of those scopes in their 50 ohm mode may not be as perfect at 50 ohms as you might expect. A little bit further into the high frequency loading effects, and on this slide here I'm showing you something which is actually equally applicable to any kind of instrument with an input impedance which is not purely resistive, not just oscilloscopes. And one issues here I've already explained, which is the effect of the parallel capacitance across a 50 ohm termination. So let's just start off by looking at the left-hand side of that slide there. We're starting off by looking at a 50 ohm source. And the reason we're interested in a 50 ohm source, signal source, is that they're often encountered in some kind of measurement situation. But when we're considering calibrating that scope, the oscilloscope calibrator, certainly the level sign generator and the for high frequency bandwidth testing, and the fast pulse edge generator will be a 50 ohm source. So the effect of putting that into the scope input, there will be the resistive effect of the input resistance, which is quite high. A typical scope at 1 megohm, the effect of the resistance is negligible. 1 megohm in parallel with the 50 ohm impedance of the source gives a 50 part per million error, which is quite negligible in comparison to a typical scope accuracy specification. The problem is the input capacitance, and the input capacitance will effectively form a low-pass filter and will create apparent bandwidth effects by that filter and the size of the capacitance moving the corner frequency of the filter. And of course, we want to make sure all our 50 ohm systems are properly terminated. So the situation shown in the bottom diagram there would be this, where we would have a 50 ohm termination inside the scope if it's one of those switch scopes, or if not, if it's just a 1 megohm input scope with no switching, we have to terminate our generator in the correct impedance anyway. So the same issue arises, that parallel capacitance there in parallel with the 50 ohms of the terminator and the 50 ohms of the source, which incidentally, like 20 ohms, from capacitor and the bandwidth point of view, the voltage source itself in that equivalent circuit there, which is a classic Thevenin equivalent circuit, the voltage source has a 0 impedance, so the two ohms are in parallel. Take a look at the chart on the right-hand side, and you'll see what I mean by the equivalent bandwidth. What I've done there is plotted out the response of circuit for different values of capacitance. Assuming a typical value of 25 picofarads, that might be the sort of thing we get for one of the lower frequency scopes, maybe in the sort of 50 to 100 megahertz region. First of all, if we don't terminate with a 50 ohm on that upper diagram, then the voltage that we actually see is twice the voltage that we would expect from the calibrated value of the source, because the source is calibrated into a 50 ohm load. Without that 50 terminator being present, you get the output voltage. So the unterminated, that's the red line. And in this case, we would see an apparent bandwidth of 129 megahertz. If we terminate correctly with the 50 ohms, we see something close to 260 megahertz. That's the green line. If we terminate if we reduce the capacitor to nth of its value down to 2.5 picofarads, the apparent bandwidth goes up by a factor of 10, and it comes out at 2.6 gigahertz. That's the blue, and you can just about see it at the top right of that picture. So these kind of loading effects are very important, and obviously when we are calibrating the oscilloscope, if there's any capacitance on the input, that effectively been calibrated out as part of the overall performance of the and setup of the instrument. Now think about those 50 ohm inputs when we have a 50 only input scope. Indeed, when we have a scope that's a switch scope, switched into its 50 ohm input condition. The issue here now is that we're sort of moving over into the RF and microwave world, where we need to think about mismatch problems. As I said earlier, you need to make sure your system, if it's a 50 ohm system, is correctly terminated all the way through with 50 ohm matches. And if you have a mismatch, a poor VSWR, and for those of you that are not familiar with these terms, VSWR is voltage standing wave ratio. It's a measure of match, or more proposed mismatch. A perfect match has a VSWR of 1, and any number greater than 1 is a progressively worsening match. Now, to give you some kind of indication, I've included some VSWR specs there for some typical scopes of the higher frequency types of a gigahertz and above. And most of these high frequency scopes, once you get above a gigahertz, are 50 ohm only. I do still see switched impedance 1 megohm and scopes at gigahertz. You can see I've got those VSWR specs there from the data sheets of those scopes. So it is typically specified, certainly for a 50 ohm only scope, may not always be for a switch scope, and often you will only have a typical figure. And that's a bit of a problem to us as metrologists, because we need to know what that, ideally we need to know exactly what our match conditions are, so that we can do an uncertainty calculation based on the mismatch error. Or we need to have a limit value that we have some confidence in. So having a typical spec isn't particularly helpful, but I'll discuss more of that in the later this series, which will be presented at a later date. In case that VSWR value actually varies frequency and with the sensitivity or the voltage division setting of the oscilloscope. And the reason you'll see also on this slide, if you look at that sort of salmon pink coloured box on the left-hand side of the slide there, you will see some of the reasons why the VSWR varies. It tends to get worse with increasing frequency, and it tends to get worse with increased sensitivity setting, with lower volts per division. So it changes with the ranges and the input attenuator settings of the scope, and that's because there's an effect of the input attenuators, as they effectively are, padding off the input circuits, which are the electronics, which are active components in the them which tend to have a much worse match and can worsen the match quite severely. So when you're operating at the most sensitive ranges of the scopes and going almost directly straight into the input amplifiers or the input samplers, then the match deteriorates. Another reasons why the match has changed with frequency and voltage level, are due to things like the passive components in there. They will cause frequency-dependent errors, the capacitive dielectric losses, which includes the parasitic capacitances of the PCB materials, as well as the actual capacitors in the input circuits. Plus, as I've mentioned already, the semiconductor devices are extremely nonlinear. And there's the fact that we actually benefit variable capacitance diodes, varicap diodes, where the reversed biased PN junction exhibits a capacitance which is related to the voltage across reverse voltage across the diode. There are diodes in diode networks in the samplers, in sampling scope, and there are also other semiconductor junctions in the input amplifiers and so on in regular scopes, and to varying extents the input capacitance will change with voltage level and with signal voltage level. So it can be a variable, and it is an issue that we have to cope with in various aspects of the calibration, including the uncertainty analysis. So we've got to the first point of to take any questions. So I'll just hand over to my colleague Rich and see if we have any questions that are forthcoming so far.
Okay. Well, good job, Paul. I don't have any questions that's come in as of right now. Let's ask again. Does anybody have any questions they'd like to ask Paul to this point? If you go ahead and type them in the chat window, we can answer them. Coming in, if any comes in, I'll let you know.
Okay, we'll just encourage anybody thinking about making a comment or question, please do so. It does make it quite interesting for us to respond to those comments and questions. And as Rich says, you can do so at any time and pick them up a bit later on. So let's take a quick look at some of the issues surrounding calibration. And here you'll see I've listed down the left-hand side some of the and characteristics of scopes that we would typically want to include in a full and complete calibration. And how would we know what's a full and complete calibration? Well, there are several places we can turn to. Clearly, there is any recommendation that the manufacturer may put into their published literature, their handbooks, calibration verification, performance test procedures for the oscilloscope. A good reference is any specifications and characteristics contained in the specifications and datasheet for the scope. Plus, there are some other guidance documents around. I've got a picture on that slide there of an EA guide. That's rather an old picture, unfortunately. That document has recently gone through a revision and re-release. I believe it's also available as a VDE. There are some other helpful documents around from various test equipment manufacturers, ourselves included. Fluke has produced a guide to oscilloscope calibration, and you also see on that slide there I've hinted at the existence of an application note on this very topic of bandwidth calibration. You might find interesting because it talks about similar things to those that we're discussing today. There are a number of tests to be performed, and there are a number of calibration signals that are required to perform those calibrations. And of course, nowadays, the most common tool for doing that job is, in fact, an oscilloscope calibrator. In the past, you might have had to have used individual items of test equipment, but nowadays there are a variety of different solutions available. Of course, many of those solutions come from ourselves. There are others as well that you might encounter. And on here, I'm portraying the role that the oscilloscope calibrator provides as a link between national standards and the unit under test oscilloscopes that we're calibrating, so that we can provide this unbroken chain of traceability from that standards to the test equipment and on, of course, to whatever tests that they are performing. And that's very key link, because the oscilloscopes measure a variety of different calibrating the oscilloscopes. We need a variety of different parameters, and some of the key parameters I've depicted there, where we're talking about peak-to-peak voltages, we're talking about frequency and time, rise time, resistance and capacitance, whole variety. And to calibrate the oscilloscope using those standards for parameters directly would be quite a difficult task. And by providing all of the functionality in the calibrator and calibrating the calibrator, the user of the calibrator have to do that calibration themselves. They can, if they wish, if they want to support the calibrators themselves, or they can use the services that the manufacturers, ourselves, and our other manufacturers in the this would provide. The users having to go through all of the complex procedures and metrology, which in many cases, certainly in terms of the peak-to-peak voltage and rise time, is quite difficult. High-frequency peak-to-peak voltage is a difficult parameter to measure and establish traceability when you have to think a little bit about the higher frequencies being an RF and microwave measurement, where the standards are always maintained in terms of power. And impedance comes into the conversion to voltage, as well as some other considerations as well, and that's quite tricky. Those are the sort of things we'll be exploring in the third topic in this series, which will be presented at another time. So the oscilloscope calibrator provides that vital link. The operated, the front panel user interface and the remote interface is actually called in terms of the units that the oscilloscope is actually measuring. That makes the whole job a lot easier, because calibrating and indicating in the terms. I'm on that number of different solutions available, the high performance oscilloscope calibrators, and some simpler solutions that have some benefits in terms of flexibility. So on this slide here, I'm showing that in a bit more detail, where on the left-hand side you have the dedicated oscilloscope calibrators, which are more appropriate to the higher performance oscilloscopes and the higher frequency oscilloscopes. And on the right-hand side, we have the multi-product or multi-function calibrators that also have scope calibration options, which give us scope calibration capability alongside some other workload coverage. And the difference there is that the multi-function calibrators have a scope cal facility, which is basically a single channel capability. They have the required signals. They may not go as high in frequency or as fast in the rise time of their edges, but they have all of the functionality, but at a single channel. Left-hand side, the dedicated oscilloscope calibrators have multi-channel capability. So they can provide the output to a number of different channels, up to 4 or 5 channels, including all the trigger signals. So the automation of the oscilloscope calibration can be much more effective by having a complete hands-off calibration without having to change the leads over to the various channels for a multi-channel oscilloscope. Now, you might notice it's got a couple of products with some grey backgrounds there, because there are some products that are no longer current products, they're obsolete products, but they're commonly used in the labs as you travel around and see what people are using to perform their calibrations. You will see instruments like the 5820 multi-channel calibrator and the 5500 series, and even some of the 9100s being worked on in the labs. And the principles and practices we're talking about here are equally applicable to any and all of those. And you'll see here some of the ranges of the frequencies of level sine wave that they can produce, and the speeds or times, rise times, if you like, of the edge signals from those calibrators. On this slide, one thing to mention just briefly, down at the bottom left of that slide in the light yellow box there, it is sometimes possible, you might think, to multiplex a single channel calibrator or the cal option single channel into a multi-channel under test scope. But that's something to be undertaken only if you're up for the metrological challenges involved, because switching high-frequency signals, switching fast edges without degrading them is very difficult to do, especially when there's cables involved, as well as the types of relays and switches you might need to use. You might be able to characterize some of the effects, but prove that they've been characterized correctly is, as I said, quite a difficult metrological challenge. So the multi-channel oscilloscope calibrator would probably be a more effective solution, unless you happen to be one of those higher level labs where you have the necessary expertise and resources to be able to undertake those tasks.
There was a question that came in. It says, will this course or later course in the series address all the factors you consider that play into the potential uncertainties? You mentioned VSWR plays into a part of the uncertainty calculations.
The answer is this particular presentation will mention a number of them, but it won't do in detail how to evaluate them or how to combine them. I would advocate that you can turn to a couple of places if you're interested in doing that. For the third presentation in this series, we'll talk about the specifics related to bandwidth calibration. That will be very much a high-frequency type of presentation, and we'll talk about high-frequency effects and be just an RF and microwave session. Now, there are already some RF and microwave web seminars available that talk about issues like mismatch, VSWR, and uncertainty budgets, how you should treat the contributions, and those specific examples are included that are available on-demand web seminars right away. So there are some resources where you can go take a look away, and we'll be including many of them in the later topic. You can see today, some I'm afraid you'll just have to wait a little bit longer for, and I hope that is a satisfactory answer to the question.
Thank you, Paul.
Okay, let's carry on now and actually talk about the calibrations themselves. And the first one is bandwidth. Now, there's a simple concept. We recognize bandwidth as the frequency at which a response drops to dBs below the response at a low frequency, some reference frequency. And in the case of oscilloscope calibration, that's usually 50 kilohertz or 10 megahertz. The reference frequency for the performance of the scope will be listed in its specifications. 50 kilohertz is usual for the older or lower frequency type scopes. 10 megahertz is more common for the higher frequency type scopes. So bearing in mind we're looking at voltage for the response of the scope, that's 3 dB corresponds to 70.7% of the high frequency response drops to 70% of the low frequency value. Now, what I've shown you there is a nice, well-behaved frequency response with a 20 dB per decade roll-off slope, which is the classic single-pole filter. In other words, a simple RC low-pass type situation. That may or may not be the case, as we'll see later on. So the actual test procedure is really quite simple. You apply the ref frequency, and then you either adjust the frequency until the displayed signal reduces down 90% of the original value at the reference frequency, or you can go ahead and dial up the nominal bandwidth frequency to see that the that's being displayed is at 70.7, alter than 70.7% of the display at the reference frequency. Now, of course, you can use the amplitude measurement capabilities built into the scope nowadays. You can do that using cursors or some other kind of signal amplitude measurement capability, which make the job easy. In the good days, when we had CRT oscilloscopes, the graticule of those scopes would have engraved on them some useful markers at the 70% level, which on the screen is typically the 100% would be considered as plus and minus 4 divisions. In other words, 8 out of the 10 vertical divisions available. So the 70.7 is at sort of 2 and a bit divisions, and even some of the LCD display scopes still put little lines on the screen at the full 20 dB per decade roll off. The scope may have some peaks and dips in its frequency response, such as you see there in my figure on the left-hand side. Actual example on the top right of that slide there is a scope I actually measured. That's a 1 gig scope, typical sort of 1 gigahertz DSO, and I measured the frequency response, and you can see there that is a little bit sort of bumpy and wiggly. And the issue for us is twofold. First of all, as I said earlier on, the reason for this is that there probably is some compensation in there so that the 50 ohm of the scope isn't degraded too badly by the capacity of the input stage. But so as metrologists, we'll be wanting to think about what's the uncertainty with which we can measure that bandwidth. So we've got to translate a voltage measurement into a frequency, because uncertainty in the signals that we're applying, the accuracy with which the oscilloscope calibrator produces those signals at the low frequency, at the high frequency, translate to a voltage uncertainty that then turns to a frequency uncertainty through the slope of the response at the measured 3 dB point. It would rash to assume that's a nice well-behaved response, as you can see evidence in the measure that I've got at the top there. And it happens that same effect of understanding whether or not we have a nice well-behaved response or something else will also have some bearing on how we might be able to employ last pulse rise time measurement to determine equivalent bandwidth later on in just a few minutes' time. So think about a few of the measurement considerations and implications from that. I already talked a bit about the traceability and units conversion issues in my introduction, with that showing the providing a vital link between national standards and the unit under test oscilloscope in terms of the traceability chain and the unit conversion process. Using an oscilloscope calibrator makes that very easy because it, as I said, provides all of the necessary signals directly in terms of the oscilloscope's readout. Otherwise, for example, if you were measuring at higher frequencies and using a regular signal generator, you'd have to do those conversions from watt or dBms or millivolts into voltage peak to peak, which would be, let's say, not so simple. As I said, we'll be discussing that later in the topic that you see there in another one of this webinars. Now, impedance and loading is another issue which we've already touched on, and again is mostly relevant to those 1 megohm inputs, where we've got to use the appropriate practice, and is making sure that we have a 50 ohm which must be terminated with a 50 ohm load. In the photographs I've got, images on the top right of the slide, you'll see a couple of different situations there. You'll see towards the bottom one of the single channel multi-product types oscilloscope calibrator options being used to calibrate a scope. if that oscilloscope is being used to calibrate the scope with a 1 megohm input impedance, the 50 ohm source in the calibrator and the 50 ohm cable that's used to transmit the cable into the scope has to be correctly terminated at the scope input. So you must use a coaxial feed-through 50 ohm terminator at the end of the cable directly at the scope input. Now, in the case of the 9500 oscilloscope calibrator, that's not an issue, because the actual circuits that are providing the 50 ohm generator are inside the active heads, deliberately so, because we want to minimize any transmission line lengths between the output of the oscilloscope calibrator and the input of the scope. But if the scope is a 1 megohm type input, then have to terminate that source that's inside that head, which is a 50 ohm source, with a 50 ohm load. And that's very easy, because inside the active head, not only do we have the 50 ohm source, but we have an internal 50 ohm load. So switch that on, and the source will be nicely terminated straight into the scope's 1 megohm input impedance. So in the case of the 9500 oscilloscope calibrator, if you can set a calibrator for 1 megohm scopes, it switches that impedance in. You don't have to worry about fitting a terminator, so it can be completely hands-off. And of course, we now have to worry about the 50 ohm inputs, either a 50 ohm input only scope, or when the scope is in its 50 ohm mode and the calibrator is in its 50 ohm mode, how well do those two 50 ohms match, and what are consequences? And as I've said, we need to make sure that we match if we have got a cable involved, and that would be with the 5820 channel calibrator as well. You'll have to terminate at the end of those cables. And typically the calibration of the calibrator itself takes place with the terminator in place, so that the effect of the terminator can be calibrated out as well. So for the 5820s, 5500 series, 9100 calibrators, calibrators are supplied with precision cables and also supplied usually with a terminator. So it's good practice to use them as they are supplied. The element here that's worth making before we go on to consider a bit more about the mismatch errors is the BNC connector. Now, the B connector is commonly used in oscilloscopes, and surprisingly, it's used all the way up to a frequency of 1 gigahertz, even though BNC connector is not thought of as a precision metrology RF and microwave connector. I guess it's there for sort of historical reasons, and it's used, but some things to watch out for. It is possible that the connectors get worn. They're not particularly good for match, and so the connectors that are used on these cables and on the outputs of the 9500 heads, specifically the 9500 heads, are a special custom BNC that's extra precision to provide the necessary robustness and repeatability, because repeatability is one of the biggest sources of uncertainty, along with mismatch in RF and microwave calibration. And bearing in mind, once we get up of a few tens of megahertz, we are very much into the domain of RF, and at the higher frequencies of a gigahertz or so, we're into the realm of microwave calibration. So all of those things become important. At the effect of mismatch. Now, I've given there on that slide, at the top right, they are the classic mismatch equation, where the top one is expressing mismatch error in terms of voltage, bearing in mind voltage is related to power by square law, and if you're an RF and microwave guy, seen a slightly different form of that, but essentially the same thing, just transferred into voltage. And it uses the symbol gamma. Gamma S and gamma L are the source and load reflection coefficients. Now, reflection coefficient is just another way of describing match from source match for the load and is related to the VSWR. So you've got the one turning VSWR into reflection coefficient. We'll deal with all of the that in a separate presentation. But the key thing here is that there is an effect. It's effect due to the source impedance of the frequency sine wave source in the calibrator, any in cables or terminal lines, and also the oscilloscope itself. Now, this is the oscilloscope, and it has its input characteristics, and as designers of a calibrator, we have no influence as metrologists hooking up the two items with practice with the best thing we can, and that is to make the source impedance, the source match of the source within the calibrator as good as possible in order to minimize the uncertainty in the peak-to-peak voltage. And that's what we see on that chart down at the bottom of that slide, that graph chart there. We actually plotted out the uncertainty that's due to mismatch for the 9530 head. That's a particular output match. Its VSWR is actually specified in the specifications for the 9500, but we try and make the job simpler for the users of the 9500 by actually writing its specifications and including the uncertainty due to mismatch in the specifications of the calibrator. So you can look at the specifications for different values of unit under VSWR, and we specify for two different values of 1.2 and 1.6, and I've included some additional values as well on that chart. The reason there's a step change at about 1500 megahertz, 1.5 gigahertz, is that the VSWR spec for the calibrator, the 9500, changes at that point. And what you see there is the overall effect of that mismatch. As the VSWR increases, as is evidenced in that chart, several percent in terms of uncertainty. The reason that's important, just to remind ourselves, is we want to look at the uncertainty of the bandwidth frequency, so we have to be able to relate frequency to voltage. We need to know the uncertainty of the voltage and get the uncertainty of the frequency. And remember my previous chart, diagram chart as well for real unit under test measurement of the amplitude versus frequency response, which had those pips. It's sort of real that you might expect about a 2-to-1 relation between flatness and a unit under test bandwidth. That's the sort of figure you might expect to see. I'm not suggesting you always assume that. In fact, I would advocate that you need to be sure what the input, what the frequency response characteristic of the scope like, and maybe just explore a couple of frequencies either side of the nominal bandwidth frequency just to get a feel for that slope if you do want to actually determine the uncertainty of the measurement around there and be thorough with your metrology. But this gives you an indication of the kind of coefficient as it turns out. For those of you that are familiar with the uncertainty analysis process, that's what you're looking for. Break. We are actually running a little bit over our time. I apologize for that. There's lots of information to convey here, so we're probably going to run over the allotted hour by a few minutes. So I hope that's not a problem. If you need to leave, just a reminder, there is recording being made, and there will be a link sent out to you where you can access that recording so you can go back and catch up with anything you missed. But I'm hoping that we're not going to overrun by too much. So let's see if Rich has got any questions for me.
A question that came in, going back a couple slides, the question is, where do you define cutoff between low and high frequency to determine what reference frequency you use?
That's a good question. And I'm guessing where I sort of said low frequency scopes tend to use a 50 kilohertz reference frequency, and higher frequency scopes tend to use a 10 megahertz reference frequency. And I would answer this way: you take a look at the oscilloscope spec, because its frequency response is normally defined in some way, and it would state the frequency that is concerned as the reference frequency in a higher performance scope. Let me say a professional oscilloscope. If it's one of the lower cost type economy oscilloscopes, then they may not put those kind of things in the specs. And the chances are a 50 kilohertz reference frequency would apply, particularly if the frequency is, if it's a 100 megascope, then you can pretty much bet it's going to be 50 kilohertz, not 10 megahertz. 10 hertz came in really when we got up into hundreds of megahertz of bandwidth, I would guess. And of course, one very simple experiment you do is to just quickly measure the difference in the response between 50 kilohertz and 10 megahertz using a Fluke calibrator, and see if there is any significant difference. And then you'll know it probably doesn't make any difference, or it might do. And that's probably the answer I think I can give you at the moment.
Great. And there was a follow-on to that. Are 50 kilohertz and 10 megahertz considered the only reference frequency that should be used?
That's a good question. I haven't encountered any other reference frequencies in my experience. There are some reasons why the 10 megahertz was chosen, because in some conditions the traceability comes in through an RF power measurement, where that traceability itself was switching over between RF power, which is the kind of standard a power sensor or equivalent device, such as a bolometer or an RF calorimeter that would be used at national laboratory levels and so forth. Some of those devices have a low frequency cutoff frequency, where really their behavior is not very good at lower frequencies, so you can't go down in frequency. And then coming up in terms of frequency, where you're measuring what would be a traditional DC low frequency voltage is through thermal converters to measure AC/DC difference. There's a bit of a sort of a gap in the middle where these things cross over, and it's always been a bit of a troublesome area around about that crossover frequency, somewhere in between about a megahertz and 10 megahertz, where the traceability paths don't always join up as well as we'd like them to. So that's another reason why in anything that's going to go really high in frequency, a 10 megahertz frequency would be the one, and we don't really see anything in between.
Perfect. Well, that's it for me.
Let's carry on now, and thank you for those questions, by the way. Let's talk about making measurements of fast edges in the time domain. So why would we make any measurements using fast edges? Well, first of all, it's very simple. We want to actually measure the pulse response, the time domain response of the scope. We want to do that because typically it's specification for the scope, so we want to actually measure it. So we'd measure the rise and fall time, which usually the parameter that is specified. We also want to measure aberrations or check aberrations. And by aberrations, I mean undershoots and overshoots after a rising or falling edge has taken place. There may be some overshoot or undershoot before the response actually settles. If we apply a perfect square edge, there is such thing, of course, but we can get really close. If we apply that to our input, we'll see, and typically we'll see something going on after the edge transition for a variety of reasons, and there are generally specifications put on the characteristics. Why is that important? Well, that's important because increasingly, as I said earlier, oscilloscopes are being used as measuring devices. Integrity of pulse waveforms, rising and falling edges on clock and data signals is extremely important in determining the integrity and functionality of a whole variety of systems and equipment data comms and other kind of digital systems. So you really have to make sure that the test equipment is meeting its specifications so that it can be relied upon to make those measurements. And these are the sort of characteristics that will be being measured for the device that scope's being used to test. So we need to make sure the scope is actually meeting its specs. The other might want to do is that perhaps if you when you're manufacturing the oscilloscope or servicing it, you might want to do some pulse response optimizations. And finally, at the bottom here, you can see there's a comment that suggests that there's an advantage if you're making measurements in the time domain, and you have to make a time domain measurement to explore the rise time of the scope. It might be advantageous to use that same measurement, if you can, to confirm the bandwidth of the scope as well, because the two are related. So that can be convenient because you effectively get the bandwidth measurement for free, so it's a lot quicker than having to mess around with the other kind of measurements, particularly at high frequencies where there's lots of other issues, as we've hinted, not just performing the test, but performing the metrological valuation and uncertainty analysis that go with them. There's another very simple reason is that you may not actually have a high enough frequency source available, particularly for some of these higher frequency oscilloscopes. And the sampling scopes that went up into the sort of multiple tens of gigahertz, we really be able to be evaluated by this technique, because high frequency sources at those levels were often very difficult to obtain in the past, not so much these days, but there are other reasons then why you may want to use an alternative technique to the sinusoidal testing that we've already discussed. However, there are some limitations which we'll come on to, but before I do that, I just want to run quickly through some definitions and some of the language that's used for describing these pulses. There's a couple of reasons for doing that. One is because these tests are used, therefore we ought to be familiar with them. Secondly, you may see a reference to some of these terms actually on the certificates of calibration, and indeed that IEC that I specified here on this slide, IEC 60469, is in fact referenced on certificates of calibration that we provide for the 9500 series oscilloscope calibrators. So that's another reason for mentioning it. So the transition from one level to another, which is what we're looking at here, so there might be the leading or the falling edge of a pulse. The definition is that the waveform is called the baseline, the top is called the top line, and in the middle we have the mesial. We have the 10% and 90% values that we've kind of hinted at before, which form the definition of the rise time. The rise time of the pulse is the time that it takes to transition between, or the rise time of the edge, I should say, is the time it takes to transition between the 10% and 90% points, which are known as the proximal and distal points. I move off that slide there. The aberrations that we're interested in are the ones at the top, after the edge. At the bottom if it's a falling edge, of course, but they are called the post-mesial aberrations. There is also something which could occur as we shoot before the actual transition takes place. There could be some kind of pre-pulse ringing or undershoot going on, and if you sort of think of that for a moment, well, how can something happen before the edge transition comes along? That might be a bit puzzling, but if you sort of stand back for a moment and think that the way that these pulse generators work is that there's a pulse generated somewhere within the inside of the pulse generator that probably then goes through some additional circuitry before it reaches the output. So there are transmission lines and other things going on where there can be delays. There can be some talks and things like that going on. So as well as there being a pulse which is created on the inside of the instrument, it doesn't emerge until a little bit later. And if there is some cross-coupling, the coupling, of course, means that something can get out perhaps quicker than the main pulse does. So that might lead to some pre-shoot. Generally, we're not particularly interested in that. We're usually interested in the what happens after the transition, and as the transition settles out to its final value. That's why we're most interested in the post-mesial transition. Look at that slightly more closely, and these next couple of slides, I'm using an example to give you some kind of feel for the time scales that are involved in here. And in this case, we're looking at that section again just after the transition as heading up towards the final value. And that's the region where we have this overshoot, and the overshoot and the conditions will be described by some kind of specification. And usually there's a specification over a couple of different time scales. And the time scales here, when we're talking about time in this context, we talk about epochs. So this is the short epoch. And if you notice there, I've given some time values. Mesos 1 nanosecond, that's 1 nanosecond after the transition has passed the midpoint, and the rise time of that edge that we're looking at is 150 picoseconds. So we're somewhere in the region of about 10 times the base transition time when we're at that first area, and we're looking for an area which is another order of magnitude longer yet again. So we're seeing 1 and 2 orders of magnitude in terms of time longer than the actual edge transition itself. Are then interested in another effect, which is on this next slide here, which is yet another scale. This is the long epoch, a much longer time scale. And this example, it's about 500 nanoseconds, which close to another 2 orders of magnitude lot still. So there is quite a long time here between 50 picoseconds and 500 nanoseconds. There are many order of magnitudes different in that time scale, but we need to look for effects. This effect that we're seeing here is a gradual settling out to the final value. As in the slide and the previous slide, I deliberately showed a dotted line that was a little bit below that heavy, thick black center line to demonstrate that the pulse hasn't, or the top of the transition hasn't quite got there yet, or if it was a falling edge, the bottom hasn't quite got there yet. And this effect is called dribble up, could be thought of as undershoot. And there are a number of reasons for this. It's to do with the way that the effects within the transmission lines and so on that are involved in creating these kind of effects differ between their low frequency behavior and their high frequency behavior. This that happens around about the time of the edge transition is very much determined by the high frequency characteristics. Things that happen over the much longer time scale, bearing in mind we're talking, 500 nanoseconds versus 100 picoseconds, which is probably 3 or 4 magnitudes. And they're related to things like skin effect, where skin effect, a high frequency effect that changes the effective resistivity of conductors and response at high frequencies against low frequencies. So that can change the size of the edge, or the edge, but the difference between the top and the bottom changed by enough that if we look at the transition early and decide that is the final settled value before it really has settled, we can get the wrong answer for the 10% and 90% points, which means we can get the wrong answer for the rise time, and get the wrong answer for the area which we should be looking for the aberrations and where those aberrations are actually centered, and therefore either incorrectly fail or incorrectly pass a non-conforming response. Now, I said we could get the wrong value, or we could simply get a different value from somebody else that chose to use a different time scale. These things are important, and particularly we're making these very high precision, I would call them high precision pulse measurements in this very demanding high speed scenario. Okay, so how do we? Yeah, I just spotted a question coming in, which I'll go on to, and it says, is the mesial point defined at the time for the 50% transition, or at the midpoint in time between the proximal and distal points? Now, that's a very good question. These will differ for a nonlinearity direction, and that's absolutely correct. And right now, I'm scratching my head. I'm just trying to recall what that definition is, and why I'm talking here, and especially since we're running a bit late. I'll pass on that question right now, and I'll have to get back to you and let you know the answer to that one when we provide you with the info on the recording links and the PDF file. I'll actually put it onto the reference slide before I send out the slides. I think that will be the best thing to do. Back to measuring the unit under test rise time. The issue here is that the rise time we see on the scope is actually a combination of the rise time of the pulse that is being applied to the scope and the response of the scope itself. We really want to be able to remove the effect and take the effect of the actual rise time of the input pulse. And we do that quite simply because there's a relationship, which I've shown on that slide there. It's an RSS calculation, which we're quite used to in various aspects of metrology, so that we can back out the rise time of the edge and discover the actual rise time of the scope. Quite well for values of pulse time ultimately equal to the this time of the scope you're trying to measure. So in other words, you can do that quite successfully with a 150 picosecond edge up to a bandwidth of around 2.5 gigs or thereabouts. The thing that will help you very much there is if you know what the speed of your transition is. So on the 9500 scope calibrators, the edge and fast edge functions, which are the faster transition times from hundreds of nanoseconds upwards, really, with the actual calibrated rise time of the edge rather than the nominal edge speed. I have the nominal edge speed as a limit. In other words, the edge is faster than. You can't do that calculation because you don't know what the actual edge time is. Begs the question, well, do you always need to do that calculation? The answer, as you can see towards the lower half of that slide, is, well, no, not really. If the edge is fast enough, that the error that you get in the observed rise time is small enough not to bother, and that's generally reckoned to be around sort of 2%. So the rule of thumb is that if your edge speed is 5 times faster than the scope, as the rise time of the pulse is 20% of the rise time of the scope, then you tolerate that error and there's no need to worry. That means you can use, if you want to, a pulse that has a rise time value specification, and that, for example, is what you will find in the specifications for some of the other oscilloscope calibration solutions, like the 5500 series scope cal options and the slower speed high voltage edge available from the 500B. Final note on that slide is just take a look at the blue box on the right hand side there. We've been talking a lot about rise time here, and for the most part that's kind of okay, because if a scope's got a rise time spec, you will probably want to test it. And for the majority of apart from some of the really fast scopes, that's probably good enough. However, you may want to do something a little bit more sophisticated and consider the response of the scope to be an actual voltage against time response, not just quantify it by the transition time, but by looking at the actual shape for which you need voltage time data. Data set, a very long data set actually, for the response, and you therefore would be considering deconvolution techniques to extract the actual response of the scope and what the characteristic of the edge that's being applied. And that's the kind of thing we do when we're actually importing our pulse traceability from the National Laboratory to our scope calibration solutions in our standards and calibration laboratory here at Fluke, especially for those very fast edges. That's the way we actually do it, to provide an accurate, as low uncertainty assessment as we can of the rise time for the lowest or first rise time edges. So we won't be talking about that in the particular presentations. It's a little bit beyond the scope, if you forgive my pun. Right, a quick look at the specification formats for the calibrators that I've mentioned here. First of all, here's an excerpt from the 9500B specification, and I'm using this to just illustrate what I'm talking about, where you'll see, let's take a look at I think it's the middle column on that table is the specifications for the 150 picosecond fast edge available from the 9530 head. And if you run your eye down that column, you'll see right at the very bottom there, the bottom row talks about the aberrations. I think that's important. We also talk about the rise and fall time, the 10% to 90% transition time, which is normally 150 picoseconds. In other words, it's going to be somewhere between plus and minus 25 picoseconds of that nominal value, is what you expect. In other words, you'd expect to see a value between 125 and 175. The actual calibrated value appears on the display. Now, if you look at that screenshot, you'll see that is the 150 picosecond fast edge function. You can see the icon at the top left of the screen there, which says 150 ps. Down at the bottom, where I've indicated with the second red arrow, is rise time equals 149 picoseconds. So we've measured the rise time, it's 149 picoseconds, and it's accurate to within plus and minus 12 picoseconds. That's the uncertainty, if you like, of the rise time value of 49. Sometimes we just get a little bit confused by what the specifications mean. I hope that example there illustrates what's going on. This slide is just a simple from the one of the 5500 series. It's actually a 5522 specification for the F1100 option, which has a nominally 300 picosecond edge. The rise time there is specified as less than or equal to 300 picoseconds, with a plus 0 to minus 100 picoseconds uncertainty. In other words, it will never be any slower than 300 picoseconds, but it could be as fast as 200 picoseconds. That's an example of that limit value that I spoke of just a few minutes ago. So how does mismatch affect these measurements? Well, the influence of mismatch on fast edge transitions, and I just want to touch on that before we end the session. So, brief slide here. I've depicted a situation where you have a generator with its output impedance, normally 50 ohms, the transmission line, also normally 50 ohms, and a load, which of course is the input to the oscilloscope. Now, the dominant mismatch here is at the unit under test input. As we've said already, that has the greatest difference from the normal 50 ohms, and the scope VSWR increases with frequency. So take a look at the green box at the bottom of that slide, and what I'm here is to try and show how the an instant edge traveling forward from the pulse generator towards the oscilloscope actually gets reflected back and forth through the transmission line and then results in a little blip appearing at the oscilloscope end. So what you actually see on the scope display is a transition by a little blip. And the little blip is because of the the mismatch condition. And on the next slide here, I have got shots. These are actual screenshots that were taken using a real oscilloscope. It's a 150 picosecond edge being displayed in a 20 gigahertz bandwidth. And we deliberately introduced mismatches and transmission line delays to do this demonstration. So on the screen, what we've got there is a deliberate mismatch and a transmission line delay. And if you take a look at that red circle there, you will see a little blip. That's the reflection that you observe. We're just looking at, this is a falling edge returning to zero. You'll just see that blip there, quite visible. And that's the effect of the reflection. If I remove the delay to there, so we've got the mismatch is still in place, and we delay, the blip moves along towards the left and gets closer to the edge transition, actually now falls in the middle of the area that we're really interested in for the aberrations measurement. You could easily confuse that reflection for an aberration called the scope itself, when it's actually just a reflection from a mismatch. What can we do about that? Well, what we want to do is to improve the match, and if we can improve the match, then the reflections will get smaller. And the reflection or the match that's under our control, first of all, there's the pulse generator and the transmission line. So if we can make the transmission line as good as possible, that's obviously got to get the signal out of the pulse generator in our active head, as it happens, in case of the 9500, into the scope UUT input, and we make that generator source impedance as good as we can. The reflection will, when it goes back from the scope input toward the generator, the pulse generator will absorb that reflection and get reflected back out again. And that's what's happening down in the case of the bottom screen there. You will see that if you compare that trace to the trace at the top, there is a very tiny, you just about see at the same kind of time that the original reflection appeared once we took out the delay. You can see there might just be a little bit more of something going on there. It's very, very small and hardly detectable. So that means we can get a good measurement of the real aberrations of the scope and see the match disturbing us. So what that really means is that if we do have issues with mismatches from a response perspective, we don't have any problem with the measurement of rise time, but we get a problem with aberrations. That's why we have to be very careful in designing these oscilloscope calibrators and their pulse generators and the way that we deliver the signals into the scope to make sure that we have that situation where we can have all of the reflections absorbed. We do that by ensuring a good source match and minimizing the transmission lengths. Now, here's if you do see excessive aberrations when you're checking a scope, that would be a sign of big troubles. Usually, it means if you've got a big aberration, it probably means that there's a larger mismatch. It's not an aberration, it's actually a reflection coming back from the mismatch because the scope input is not really behaving very well. It's probably been damaged or blown up. So excessive aberrations are often a sign that there's something going wrong with the input. And if were you to test the VSWR, you'll find it would be very poor and out of any kind of specifications. That's a good, what should we say, health check that you can watch out for when doing these calibrations. The last part of this discussion then is, well, how can we get a bandwidth figure using fast pulse? Well, this is called imputing. way that we can calculate the effective equivalent bandwidth from the pulse response, specifically from the rise time. Now, we can do that if we know something about the rise of the response. If the response is a Gaussian response, then there is a relationship, which is a well-known relationship. It's the one I've shown you at the top of the slide there, where we can make a simple calculation from the measured rise time and translate that into a bandwidth. Now, that's true, so we can do that if we know the scope has a Gaussian response, or we've been told what the response is. And we may find that the manufacturer has been kind enough to put that into their specifications or into their handbook. I've seen those figures quoted there, so you can use a different number from the 350 as usually a different number. So take a look in the scope specs and manual and see what you can find. And then you can actually do this with some degree of confidence. If that's the case, and you can, then okay, what happens now? It got available. Well, what you do when you do have a fast enough edge available? Well, first of all, you need to consider the effect of the speed of the edge itself in comparison to the effective rise time of the scope. Exactly the same discussion as the one we just had a couple of slides ago. We can use the relationship between time and actual rise time, that RSS calculation, if we want to remove the speed of the edge, rise time of the edge, from the observed value and derive the actual scope rise time and substitute that into our bandwidth. Or we can say, well, if the edge is fast enough, the error that we're going to get is so small we don't care. So, in other words, do exactly the same thing. Ask ourselves, is the speed of the edge, the rise time of the edge from our edge generator, better than 5 times faster than the time of the scope? If the answer is yes, then we don't need to worry too much. So exactly the same thing as we did before. So what's wrong with doing that? The answer is nothing really. There's no reason why we should not do that. It's very convenient, as I said. If we don't have a suitable high-frequency source, then that's a reasonable thing to do. However, there are some things to remember. First of all, we need to be sure that we can on a relationship between rise time and bandwidth that's valid for that particular scope that we have in our hands. In other words, is it a Gaussian response, or is there a figure that's quoted in either the handbook or the specifications for that oscilloscope? The problem is that you can get an equivalent bandwidth, but you really don't get very much information on the frequency response of the scope, and that might be of interest for you. For example, as I've said, if you want to do a thorough job of evaluating the uncertainty of any kind of measurement, you might need to know what the slope of the response of the scope is. You might want to know whether you do have peaks and dips in the frequency response, and clearly you won't be able to get that with this kind of technique, but it is very convenient and useful and is effectively a measurement for free if you've already made the measurement of the rise time of scope. So to be used with caution, but very helpful in certain times. Finally, this is the last slide. There are lots of parameters appearing on the slide that we haven't mentioned, and I did mention them up front in the typical what's necessary to calibrate an oscilloscope. And the reason is that there are other measurements that very often are not made as a routine recalibration, a performance verification type measurement, might be of more interest to the oscilloscope manufacturers at the time of the manufacture or service of that oscilloscope. Such things as you see on here, where we're talking about sampler alignments, effective number of bits, and things like that. They often are of interest, and really, if you want to get a full picture of the scope's performance, well, is this sort of cross-correlation, if you like, between what you get by making a sine wave measurement and what you get by making an edge measurement, and you can sort of move back and forth between one side and the other. To get a really good picture, you kind of need to do both. So that's the point where I'd like to stop. Thank you for your attention today. Apologize for taking a little bit longer than hour that we suggested we might do, but I'm hoping that you would have found the various topics we've explored of interest. So thank you very much, and just hand you back now to Rich, see if we've got any more questions to address.
Excellent. Thank you, Paul. Very nice job, and I think that had a lot of great information, applicable information that many can use. I did not receive any further questions. If you do have additional questions or would like to reach out to us, or I can be contacted, you can contact me directly at rich.mcfadden@flukecal.com. And for your time today, and with that, we'll let you go, and we look forward to having you in a future web seminar.
Much, everybody, and these last few slides here that you'll see when you get the slide set just give you a hint of more of the resources and information that's available for you should you want to make use of them. So I'll say once again, thank you very much, and hope to see you at a future web seminar event.